Bill Gray sits in front of four monitors in a spare bedroom in rural Washington state. It is 3:47 in the morning. He has been tracking the object for 6 weeks. The software says impact in 11 days. Gray is not employed by NASA. He does not work for SpaceX, the European Space Agency, or any government. He is a retired mathematician who writes orbital tracking software in his free time. Software that has become so precise that NASA itself uses it to predict where defunct satellites will fall. And right now, his software is telling him that something is about to hit the moon at roughly 5,800 miles per hour. That part is not unusual. The moon gets hit all the time. Micrometeorites, spent rocket stages, the occasional comet fragment. What keeps Gray awake is not the impact itself. It is the object's trajectory. It is the way it tumbles. It is the fact that when he runs the orbit backward through time, tracing its path through cislunar space like a thread pulled from a knot, the math suggests it has been up there for years, possibly since 2014, possibly longer. And it is the fact that no one, no space agency, no government, no private launch provider will publicly confirm what it is. Gray makes the data public on January 21st, 2022. He identifies the object as WE0913A, a piece of debris approximately 4 meters long, probably a spent rocket upper stage. Based on orbital mechanics, he attributes it to a Chinese Long March 3C rocket that launched the Chang'e 5T1 mission in 2014. Within hours, the story goes global. Chinese rocket to slam into moon, the headlines read. 3 days later, China's Ministry of Foreign Affairs issues a statement. The spokesman's tone is carefully neutral. He says the upper stage from that mission burned up in Earth's atmosphere years ago. Gray rechecks his math. He runs the trajectory again. Then he issues a correction. He was wrong about the Chinese rocket. The object, he now believes, is a SpaceX Falcon 9-second stage from the DSKOVR mission, launched in 2015. SpaceX does not respond. NASA does not comment. And on March 4th, 2022, the object, whatever it is, hits the far side of the moon at exactly the time and location Gray predicted, traveling at 5,771 miles per hour, and disappears into a region no human eye can see from Earth. 2 months later, NASA's Lunar Reconnaissance Orbiter passes over the impact site. The photographs come back. There is not one crater. There are two. That is the part that does not fit. To understand why two craters should not exist, you need to understand what we are not being told about the graveyard forming in the space between Earth and Moon. You need to understand the object that fell. And you need to understand the treaty that was supposed to prevent this, but contains a loophole large enough to hide a decades-long secret. This is the story of the crash we witnessed. And the payload no one will name, WE0913A, was discovered on September 13th, 2020 by the Catalina Sky Survey, a NASA-funded program that scans the night sky for near-Earth asteroids. At first, that is exactly what astronomers thought it was, an asteroid. But asteroids do not move like this. Within days, observers noticed the object was in what's called a chaotic Earth-Moon orbit, a highly elliptical trajectory that loops around both the Earth and Moon in an unstable dance. Natural objects almost never settle into these orbits. They are gravitationally messy. They require very specific velocity and angle conditions. They are, in other words, the signature of something launched. Bill Gray was one of the first to recognize this. Gray is 66 years old, soft-spoken, precise in the way that mathematicians often are. He spent decades working on software for the Minor Planet Center, the global clearinghouse for asteroid data. When he speaks about orbital mechanics, he does so in the same tone you might use to describe a crossword puzzle. Calm, methodical, confident. But when you ask him about WE0913A, something in his voice shifts. "I have tracked thousands of objects," he said in an interview published in April 2022. "I have seen rocket bodies, satellite fragments, lunar flyby debris. I have never seen one that behaved like this." What bothered Gray was the object's spin. Most spent rocket stages tumble slowly, end over end, because they are essentially hollow tubes with engines on one end. Their mass is asymmetrical. This creates a predictable wobble. WE0913A tumbled differently. Its rotation period was short. Experts observed variations between 2 and 4 weeks. And the light curve, the pattern of sunlight reflecting off its surface as it spun, was unusual. It suggested the object was not uniformly shaped, or not uniformly weighted. Dr. Vishnu Reddy is a planetary scientist at the University of Arizona's Lunar and Planetary Laboratory. He has spent 15 years studying space debris, using spectroscopy, analyzing the light bouncing off objects to determine what they are made of. In February 2022, his team turned their telescopes toward WE0913A. What they found did not match the spectral signature of a typical aluminum rocket body. "We expected a very clean, very narrow reflectance spectrum," Reddy explained in a paper published later that year. "Aluminum alloys have a specific fingerprint. This object had that fingerprint, but there was something else, a secondary absorption feature we could not immediately account for." He suspected a composite structure, possibly metal with another material attached, possibly a payload still connected to the booster. By mid-February, Gray had backtracked the object's orbit as far as his software would allow. The trajectory pointed to a launch window in 2014 or 2015. 2 missions fit the profile. China's Chang'e 5T1, a lunar flyby test mission launched in October 2014, and SpaceX's DSCOVUR mission, a space weather satellite, launched in February 2015. Gray initially chose Chang'e 5T1. The orbital elements were a close match. Then an email arrived from John Giorgini, a senior analyst at NASA's Jet Propulsion Laboratory. Giorgini is one of the world's leading experts in orbital trajectory reconstruction. He is the person NASA calls when they need to know with absolute certainty where something was and where it is going. Giorgini had run his own analysis. He told Gray the object was not Chinese. It was American. It was, Giorgini said, the second stage from the SpaceX Falcon 9 that launched DSCO VR. Gray issued a public correction on February 12th. He apologized for the error. The object, he wrote, was almost certainly the DSCO VR booster. SpaceX founder Elon Musk did not confirm it. He did not deny it. He said nothing. And then, quietly, the data stopped making sense. Because when other analysts began checking Giorgini's numbers, they found something Gray and Giorgini had both missed. The object's trajectory, when traced all the way back to 2015, did not match the DSCO VR launch either. Not perfectly, not enough. On March 4th, 2022, at 7:25 a.m. Eastern Time, WEO-913A struck the moon. The impact occurred on the far side, in a region near the crater Hertzsprung, a 570-kilometer wide scar formed billions of years ago. No telescope on Earth could see it happen. No camera recorded the flash. The only witnesses were gravity and math. Bill Gray's software had predicted the impact time to within seconds. The location was accurate to within a few kilometers. By every measure, it was a flawless prediction. For 6 weeks, the world waited for images. NASA's Lunar Reconnaissance Orbiter, or LRO, has been photographing the moon since 2009. Its narrow-angle camera can resolve features as small as a meter across. But LRO does not hover. It orbits. It passes over each part of the lunar surface once every few weeks, and its imaging schedule is planned months in advance. The first opportunity to photograph the impact site came in late April. Dr. Mark Robinson is the principal investigator for the LRO camera. He is a planetary geologist at Arizona State University, cautious, deliberate, someone who has spent decades studying impact physics. When his team processed the images and compared them to previous photos of the same region, they immediately saw the crater. Then, they saw the second one. "My first thought," Robinson said in a NASA press briefing, "was that we had misidentified the location, that we were looking at two separate, unrelated impacts from different events. But the craters were fresh. The ejecta patterns were bright, sharp-edged, unsoftened by micrometeorite bombardment. Both craters had formed at the same time, and they were overlapping. The larger crater measured roughly 19 meters across, oriented to the east. The smaller one, about 17 meters, sat just to the west. Together, they formed a figure-8 pattern in the lunar regolith, like a dumbbell pressed into dust. Robinson ran the numbers. He compared the double crater to every previous known impact on the moon. Spent rocket bodies had hit the moon before. NASA deliberately crashed the Saturn V's 4B stages from several Apollo missions into the lunar surface to generate seismic data. Those impacts left single craters, always single. A rocket body is essentially a fuel tank with an engine. By the time it reaches the moon, the fuel is long gone. What remains is a hollow tube, light, structurally weak, with almost all of its mass concentrated at the engine end. When it hits, it crumples, it disintegrates. The engine, being the densest part, creates the deepest part of the crater. But it creates one crater, not two. Dr. Tanner Campbell is a planetary physicist who specializes in impact cratering mechanics. He had worked with Robinson on previous LRO studies. He stopped. He did not immediately offer an explanation. He did not speculate. He asked to see the data again. I have modeled hundreds of hypervelocity impacts, Campbell said in a follow-up interview in July 2022. I have seen double craters before, but only in very specific circumstances. Asteroid pairs, binary meteoroids, objects with two distinct, separated masses. He paused. This object was supposed to be a rocket stage, a hollow, empty rocket stage. The only way to create two craters of nearly equal size, Campbell explained, is if the impactor has significant mass at both ends. At one end, the engine. At the other end, something else. Something heavy. Robinson's team wrote up their findings carefully. The paper, published in the Planetary Science Journal, included detailed measurements, computer simulations, and comparisons to other impacts. The conclusion was measured, cautious, precise. The object that hit the moon, they wrote, likely had large masses at each end. They did not say what those masses were. They did not say what the object was. And NASA, in its official summary, referred to the object only as a rocket body. Not SpaceX, not Chinese, not American, just a rocket body. That is where the official record stops. And that is where the questions begin. There is an international agreement that governs what happens in space. It is called the Outer Space Treaty. It was signed in 1967, at the height of the Cold War, by the United States, the Soviet Union, and the United Kingdom. Today, 112 countries are parties to it. Article 8 of that treaty contains a single, critical provision. States are responsible for tracking and registering all objects they launch into space. The word responsible is important. The word required does not appear. Dr. Paul Cifola spent 41 years at M1T developing orbital prediction models for the U.S. Air Force and NASA. He helped design the algorithms that track satellites, space debris, and classified military payloads. He knows, better than almost anyone, what is being tracked and what is not. The treaty obligates nations to maintain a registry, Cifola said in a 2021 interview for a space policy journal. It does not obligate them to make that registry public. It does not obligate them to update it in real time. And it certainly does not obligate them to disclose payloads. In practice, this means that when a country launches a rocket, it files a report with the United Nations Office for Outer Space Affairs. That report includes basic information: launch date, orbital parameters, general purpose. It does not include technical specifications. It does not include what exactly is attached to the rocket. And if the mission is classified, or even partially classified, the report can be vague to the point of meaninglessness. The United States, for example, has launched hundreds of objects it describes only as payload or satellite. No further detail. China's registry is even more opaque. Many Chinese launches are reported months or even years after the fact. Some are not reported at all. And there is no enforcement mechanism, no penalty, No inspection process. You are expected to take each nation at its word. This becomes important when you try to answer a simple question. What was WE0913A? Bill Gray initially said it was Chinese, then corrected himself and said it was American. But neither government confirmed it. And when researchers tried to verify the object's origin by tracing its orbit backward, they hit a wall. Dr. Alice Gorman is a space archaeologist at Flinders University in Australia. She studies the material culture of space exploration. What we leave behind, what we forget, what we refuse to acknowledge. In the months after the impact, she tried to reconstruct the object's history using publicly available launch data. She found 13 possible matches, 13 launches between 2013 and 2016 that could have placed an object into a trajectory similar to WE0913A. Some were American, some were Chinese, some were Russian. 2 were listed in official registries with no payload description at all. Here is the uncomfortable truth, Gorman wrote in a paper presented at the International Astronautical Congress. We do not have a complete inventory of what is in cislunar space. We never have. The only objects we track with high confidence are the ones that are actively transmitting, or the ones large enough to be seen by military radar. WE0913A was not transmitting. It had been dark for years, and radar coverage beyond geostationary orbit, the band of space where most communication satellites sit, about 36,000 kilometers up, is sparse. Cislunar space, the region between Earth and the Moon, is largely unmonitored. Not because we lack the technology, because no one is required to monitor it. Gorman's research revealed something else. Between 1970 and 2020, at least 47 rocket upper stages were launched into trajectories that took them beyond Earth orbit. Most were moon missions. Some were deep space probes. Of those 47, only 22 are still being actively tracked. The other 25? Unknown. Possibly in solar orbit. Possibly crashed into the moon decades ago. Possibly still out there, dark, silent, tumbling through the gravity well, waiting to fall. The absence of tracking, Gorman said, is functionally identical to the absence of accountability. By late 2022, the debate over WEO913A's identity had fractured into camps. Some researchers still believed it was the DSCO-VR booster. Others argued for Chang'e 5 T1. A few pointed to other missions entirely. European, Japanese, even Indian. But everyone agreed on one thing. The double crater meant the object was not what it was supposed to be. Music, faint, rhythmic pulse. And no one in an official capacity was willing to say what it actually was. Rocket stages do not normally carry mass on both ends. They carry fuel, engines, guidance systems. All of that mass is concentrated in the lower section. The upper section, the part that faces space, is often just a thin metal dome, a structural cap, essentially empty, unless something is attached to it. Dr. Jonathan McDowell is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. He is also one of the world's foremost experts on space debris. He maintains an independent database called Jonathan's Space Report, a meticulous, obsessively detailed log of every known satellite, rocket stage, and fragment in orbit. When the double crater images were released, McDowell began digging. He went back through old launch manifests. He cross-referenced payload masses with booster performance data. He looked for missions where a rocket upper stage might have retained additional mass after payload separation. What he found surprised him. "There are more of these than people realize," McDowell said in a podcast interview in June 2022. Secondary payloads, ballast masses, calibration targets. Some missions carry extra weight deliberately, either for balance during ascent or for post-separation testing. He gave an example. In 2009, NASA launched the Lunar Crater Observation and Sensing Satellite, or LCROSS. The mission's goal was to impact the moon's south pole and analyze the debris plume for water ice. But LCROSS was not a traditional probe. It was a payload adapter, a metal ring with instruments attached, still connected to the spent upper stage of the rocket that launched it. The entire stack, probe and booster together, was aimed at the moon. When it hit, it created a single crater. But the mass distribution was unusual. The booster and the probe were still connected, meaning the impact involved a much longer object than a typical rocket stage. McDowell's point was simple. Sometimes, what hits the moon is not just a rocket. It is a rocket plus something else. The question then is what was attached to WE-0913A? And why was it still attached? In most missions, the payload separates cleanly. The rocket delivers it to orbit, then moves away. The upper stage, its job done, becomes debris. It either burns up in the atmosphere or drifts into a long, slow orbit around the sun. But some missions are different. Some missions require the upper stage to remain with the payload for days or even weeks, providing power, stabilization, or trajectory corrections. In those cases, the stage and payload travel together until a final separation burn. If that burn never happens, if the separation mechanism fails, or if the mission profile simply does not include one, the two remain joined. That is one explanation. The other explanation is more unsettling. Dr. Laura Grego is a senior scientist at the Union of Concerned Scientists, where she specializes in space security and military space systems. She has testified before Congress on the risks of space weapons and the lack of international verification protocols. When asked about the double crater, she did not hesitate. The simplest explanation, Grego said in a written statement, is that the object was carrying something it was not supposed to disclose. She did not elaborate on what that something might be, but her choice of words was deliberate. Not something that failed to separate. Something it was not supposed to disclose. There is a category of space missions that the public rarely hears about. They are not classified exactly, but they are not advertised either. These are missions with dual purposes: a public-facing scientific objective and a secondary, undisclosed goal. Sometimes that goal is testing new technology. Sometimes it is calibrating ground-based sensors. Sometimes it is placing an object in a specific orbit to observe how it behaves over time. And sometimes It is delivering a payload that no one wants to explain. Grego pointed to a 2014 launch by the Chinese military. A Long March rocket carried a satellite described in official documents as a technology verification platform. The satellite maneuvered in orbit, changed its trajectory multiple times, and approached other satellites. Western analysts called it a possible anti-satellite weapon test. China called it debris cleanup research. Both could be true. Neither could be proven. Once an object is in space, Grego said, it is very difficult to know what it is doing unless it wants you to know. By mid-2022, McDowell had narrowed his list of candidates for WE-0913A to 3 missions. One was Chang'e 5-T1, the Chinese lunar test flight. That mission carried a small return capsule and a service module. Official records say the capsule returned to Earth. The service module, according to Chinese sources, entered lunar orbit and later crashed. But the crash location was never disclosed. The second candidate was DSCOVR. That mission launched a space weather satellite to a stable point between the Earth and Sun. The Falcon 9 second stage, according to SpaceX, was sent into a heliocentric orbit soot, but no one tracked it after separation. The third candidate was a mission McDowell would not name publicly. In his database, he listed it only as probable classified secondary payload, unconfirmed. When pressed, he said only this: there are objects in the registry that do not match the physics, mass discrepancies, delta V budgets that do not add up. If you assume the official story is complete, the math does not work. If you assume there is something else aboard, something with its own mass, its own fuel, it works fine. He did not say which mission. He did not say which country. But he did say this: the double crater is not an anomaly. It is a confirmation. Dr. Tanner Campbell did not want to speculate. He wanted to model. In the weeks after the LRO images were released, Campbell and a team of researchers at Purdue University built a series of computer simulations. Their goal was simple: reproduce the double crater using realistic impact parameters. They started with the assumption that WE-0913A was a standard rocket upper stage. They used dimensions and mass estimates based on the Long March 3C and Falcon 9 second stages, the two most likely candidates. They programmed the object to hit the moon at 5,771 miles per hour. The velocity Bill Gray had calculated at an oblique angle of roughly 15 degrees. The simulation ran. The rocket hit. A single crater formed. They tried again, adjusting the angle. Single crater. They tried different impact velocities, different surface compositions, different rotation rates. Every time, single crater. Then they changed one variable. They added mass to the front of the rocket. Not fuel, not structure. A discrete, solid mass, approximately 1,200 kilograms, bolted to the nose. They ran the simulation. 2 craters. Campbell ran it again. He adjusted the mass to 1,000 kilograms. Still 2 craters. He tried 1,500 kilograms. 2 craters, slightly different sizes. The sweet spot, the mass distribution that most closely matched the actual craters on the moon, was approximately 1,300 kilograms at the front and 1,100 kilograms at the back, the engine. Total mass, roughly 2,400 kilograms. A standard empty rocket, upper stage, weighs between 800 and 1,200 kilograms. The object that hit the moon was twice as heavy as it should have been. We ran this simulation 60 times, Campbell said in a presentation at the Lunar and Planetary Science Conference in March 2023. We varied every parameter we could think of. The only way to produce two craters of roughly equal size is if the object has two distinct mass concentrations, separated by a low mass section. He showed a diagram. It looked like a barbell, engine on one end, unknown mass on the other, hollow tube in the middle. Then he showed a comparison. On the left, the simulated double crater. On the right, the LRO photograph. They were nearly identical. The room went quiet. Someone in the audience asked the question everyone was thinking. What was the mass? Campbell's answer was careful. We do not know. Our simulation does not tell us composition. It does not tell us purpose. It only tells us that the mass was there. Another voice from the audience. Could it have been residual fuel? Campbell shook his head. Unlikely. Fuel sloshes. It redistributes on impact. It does not create a clean, discrete secondary crater. What we are seeing is consistent with a solid, rigid mass. Could it have been structural? Part of the rocket itself? Not in any design we are aware of. The moderator stepped in. The session moved on. But after the panel, several researchers approached Campbell privately. One of them was Dr. Vishnu Reddy, the spectroscopist from the University of Arizona. Reddy had been bothered by the light curve data for months. The way the object reflected sunlight suggested an asymmetrical shape or an asymmetrical coating. He had assumed it was paint or thermal blanketing, something cosmetic. But Campbell's simulation changed his interpretation. If there is a second mass, Reddy said in a phone interview weeks later, then the light curve makes sense. We were not looking at a rocket with an unusual surface. We were looking at a rocket with an attachment. He paused. The question is whether that attachment was deliberate or incidental, whether it was cargo or equipment or... He did not finish the sentence, but the implication was clear, or something else entirely. Music, sustained, ominous tone. By the spring of 2023, multiple independent research teams had reached the same conclusion. The object that struck the moon was not a simple spent rocket stage. It was a composite structure, rocket plus payload. And the payload had remained attached, deliberately or otherwise, for years. But no space agency confirmed it. No government claimed it. And in the absence of an official answer, the theories began to multiply. Some researchers believed it was a failed separation, a mechanical malfunction that left a satellite or probe stuck to its booster, drifting, until the moon's gravity finally pulled it down. Others suspected a classified military payload, something the launching country did not want to acknowledge. A few pointed to the possibility of an entirely misidentified object, not from 2014 or 2015 at all, but from an earlier mission, something lost decades ago and only now rediscovered. And then there was the theory that no one wanted to say out loud, that the object was exactly what it was supposed to be, that the attachment was not a mistake, that whatever hit the moon was placed in that orbit, with that mass, for a reason we were never meant to know. Bill Gray stopped updating his blog about WE0913A in May 2022. Not because he lost interest, not because the story was over, because, he said, he had learned everything the data could teach him. I predicted the impact. I was right about the time and location, but I was wrong about the object itself, Gray said in one of his final posts. I thought I was tracking a piece of known debris. What I was actually tracking was something unaccounted for. He did not retract his identification. He simply acknowledged the uncertainty, and then he went quiet. For someone who had spent months publicly analyzing the object, posting updates, engaging with other researchers, the silence was conspicuous. In a private email exchange later that year, Gray explained his thinking. At a certain point, he wrote, you run out of evidence. All you have left is speculation. And speculation, no matter how educated, is not the same as data. But others were less willing to let it go. Dr. Alice Gorman, the space archaeologist, began reaching out to space agencies directly. She filed Freedom of Information requests with NASA, the European Space Agency, and the China National Space Administration. She asked for any records related to objects in cislunar space between 2014 and 2020. NASA's response arrived 4 months later. It included a list of known lunar missions, all of which were already public. No additional objects were identified. The European Space Agency responded similarly. China did not respond at all. Gorman also contacted SpaceX. She wanted to know if the company had tracked the DSCOVR second stage after launch, and if so, whether they could confirm its final trajectory. SpaceX's media team sent a one-sentence reply. We do not comment on post-mission orbital debris. That sentence is worth pausing on. Not, we do not have that information. Not, the stage burned up in the atmosphere. We do not comment, which implies they could comment. They simply choose not to. Gorman found this response telling. Silence in space policy is a position, she said in an interview. It is not the absence of an answer. It is the answer. By late 2023, the story had largely disappeared from public view. A few academic papers continued to circulate. Campbell's impact simulations were cited in several journals. Robinson's double crater images became a standard reference in lunar geology courses. But the mainstream press moved on. The object was no longer news. And yet, among a small group of orbital analysts, the question remained. In private Discord servers and email chains, researchers continued to share data. They tracked other unidentified objects in high orbits. They compared light curves, spectral signatures, trajectory anomalies. They found more, not dozens, not hundreds, but more than 0. Objects in orbits that did not match any known launch. Objects with mass distributions that defied standard rocket geometry. Objects that had been up there, dark and silent, for years. One researcher, who requested anonymity, describe the realization this way. You start thinking WE0913A is a one-off, a mystery. Then you look closer and you realize it is not an outlier. It is an example. There is a term used in astronomy, selection bias. It refers to the tendency to find only what you are looking for. If you are scanning the sky for asteroids, you catalog asteroids. If you are tracking active satellites, you log active satellites. But if you are not looking for dark, unregistered objects in distant orbits, you will not find them until one of them falls. And when it does, if it lands somewhere no one is watching, like the far side of the moon, it disappears. No crater photos, no analysis, no questions. The only reason we know about WE0913A is because Bill Gray happened to be looking, because his software happened to catch it, because NASA's Lunar Reconnaissance Orbiter happened to pass over the impact site at the right time. If any one of those factors had been different, the object would have hit, and we would never have known. Dr. Paul Cifola, the MIT orbital analyst, put it bluntly. Cislunar space is not monitored the way people think it is. We see some things, we track some things, but there is a lot of dark sky and a lot of dark objects, and no requirement to shine a light. In January 2024, the United Nations Office for Outer Space Affairs published its annual report on space debris. The section on cislunar debris was 3 paragraphs long. It mentioned the March 2022 impact in a single sentence. An unidentified rocket body impacted the lunar surface, producing surface disruption consistent with previous such events. Unidentified. Not Chinese, not American, not SpaceX, not Chang'e. Unidentified. And that, apparently, was considered sufficient. Here is what we know. An object spent years in the space between Earth and Moon, untracked, unacknowledged, until it finally fell. When it hit, it created 2 craters, indicating a mass distribution inconsistent with a standard rocket stage. Computer simulations suggest it carried roughly 1,300 kilograms of additional mass at its forward end, mass that no space agency will identify. Despite months of investigation, no government has claimed the object. No launch provider has confirmed its origin, and the international body responsible for tracking space activity has classified it in official records as unidentified. Here is what we do not know: what the object was, where it came from, what it was carrying, why it was left in orbit, whether its presence was an accident or intentional, and whether there are others like it. But there is one thing we can say with certainty: this will happen again. Dr. Jonathan McDowell's database currently lists 84 rocket bodies in high Earth orbit or beyond. Of those, 29 have not been actively tracked in over 5 years. Some are likely in solar orbit, drifting away from Earth. Others may have already impacted the Moon, unobserved, but several, McDowell estimates at least 6, are in chaotic Earth-Moon orbits similar to the one WE0913A followed, which means they will fall. Not this year, necessarily. Maybe not for a decade. Orbital decay in cislunar space is slow, erratic, influenced by the sun's radiation pressure, the Earth's irregular gravitational field, the moon's pull. But gravity is patient, and eventually, these objects will come down. When they do, we may learn what they are. We may find more double craters, more mass anomalies, more unanswered questions. Or we may learn nothing at all, because the impacts will occur in places we are not looking. There is a deeper question beneath all of this. It is not a question about WE0913A specifically. It is a question about what we have allowed cislunar space to become. For decades, the space between Earth and Moon was seen as empty, unimportant, a void to pass through on the way to somewhere else. Missions launched, rockets fired, payloads separated, or did not. Stages drifted into high orbits, and we stopped thinking about them. But cislunar space is not empty anymore. It is becoming a junkyard, a graveyard, a place where the things we launched and forgot are beginning to accumulate. And because there is no international requirement to monitor it, no enforcement mechanism to track it, no penalty for leaving things behind, we have no comprehensive map of what is out there. We are flying blind. Dr. Laura Grego, the space security analyst, has been warning about this for years. People think of space debris as a low Earth orbit problem, she said in congressional testimony in 2023. They think of dead satellites, paint flecks, collisions at 17,000 miles per hour. And that is a real problem. But we are also creating a secondary debris field in deep space, and we are doing it with almost no oversight. She paused. The difference is that in low Earth orbit, debris eventually falls and burns up. In cislunar space, it just stays there for years, for decades, until gravity or a collision brings it down. And when it does come down, if it hits the moon, we might get lucky and see the crater. But if it hits something else, a future lunar base, a crewed spacecraft, a fuel depot, we will not get a second chance. The Artemis program, NASA's plan to return humans to the moon, is scheduled to land astronauts on the lunar surface in 2026. China has announced plans for a permanent lunar research station by 2030. Private companies, SpaceX, Blue Origin, Rocket Lab, are developing lunar landers, cargo missions, refueling infrastructure. In the next decade, cislunar space will go from a frontier to a highway. And somewhere in that space, right now, there are objects we cannot see, tumbling in orbits we have not mapped, carrying mass we cannot identify. They are already there. We just have not watched them fall yet. Bill Gray is still tracking. His software still runs, scanning orbital data, flagging anomalies, predicting impacts. In a blog post from February 2024, he mentioned, briefly, that he had identified another object in a decaying lunar orbit. He did not name it. He did not attribute it to any country or mission. He simply noted its trajectory, calculated the impact window, and posted the data. The object is expected to hit the moon sometime in late 2025. Same region. Far side. No cameras. No witnesses, just math and gravity and silence. The crash we witnessed was not an accident. It was a consequence of launching without tracking, of registering without disclosing, of building an international framework for space exploration that depends entirely on trust, and then trusting no one to follow it. WE0913A is not an anomaly. It is a preview. The double crater on the far side of the moon is not a mystery. It is a message. It tells us that we do not know what we have put into space, that we are not keeping track, that the objects falling from the sky are heavier, stranger, and more numerous than we want to admit. And it tells us that the next time something falls, we may not be looking. Here is what I want you to think about. Right now, above your head, there are objects in orbit so high and so chaotic that no one is watching them. Some of them have been there since before you were born, and some of them are not supposed to exist. When the next one falls, and it will fall, what do you think it will turn out to be? Leave your answer in the comments. I want to know what you think is out there. If this is the kind of story that makes you question what you have been told, subscribe. There are more, and they are closer than you think. Next time, we are going underground. There is a network of tunnels beneath a city in Eastern Europe that was sealed in 1953. Last year, a construction crew broke through. What they found was still running.